accepted.
Hi everyone, my name is KK and I work in NVIDIA. I will sit down today because I'm an engineer. In my talk entitled From Backpropagation to Enterprise Deep Learning, we will cover backpropagation up to enterprise deep learning. And if you are surprised that my title was misleading, so I'm really sorry. The journey from backpropagation to enterprise deep learning is like 5 years of academic knowledge and probably another 5 years of professional experience. We have 50 minutes, so I need to be fast. And by the way, you must have heard that in NVIDIA we do a lot of deep learning because we can. And backpropagation is a fundamental algorithm of every deep network. And backpropagation is like pregnancy. Only a mother truly understands pregnancy. And similarly, only a neural network truly understands backpropagation. So we will start with an experiment where we will all experience backpropagation ourselves to better understand it. You will be neurons, and I will fire at you some signals. And your job is to respond 1, then you raise your hand, or -1, then you nod negatively. Let's practice. 1. Perfect. And -1? Not perfect. Again, -1? Okay, better. Also, please prepare your wallets, because for each wrong answer, everyone pays me 10 Polish zlotys. The organizers will collect the taca. Okay, are you ready? So I'm shooting my first training sample. 1 or -1? Okay, I see some ones. Unfortunately, this was -1. So the organizers, please collect my money from the losers. Another one. 1 or -1? Okay, I see some ones. But unfortunately, again, this is -1. So another sample training, 1 or -1? Okay, people are raising hands. That's very good, very good. More hands in the air, because this is actually 1. And I think some of your neurons already feel the atmosphere, you know? So it's time for a test. Time for a test. 1 or -1, okay? Please focus. Oh yeah, a lot of hands in the air. Ladies and gentlemen, girls and boys, you are officially trained and thoroughly tested reggae detector. Excellent. I'm very happy about that. Now a baby would need much more training. For you it was easy because you already know song genders. So in your brains actually there is not much going on anymore. No offense. But now we will write a neural network which, given a song, will itself guess its music gender, and we will write it from scratch. So if there is anyone here for whom AI is still magic, my apologies, but the spell will be broken. Maybe the coding session sometimes might be a bit painful for you, but I still strongly believe it will not kill you, it will make you stronger. But first, a few words of introduction into music. Perception of sound takes place in the spectral domain. We don't hear samples, we hear frequencies. Like, for example, this is A4, not samples, but a frequency of 440 Hertz. This is E2, 82 Hertz. Now, let's record note A, some melody, and a song in the rhythm of ska. Okay, we have it. You didn't like the song? Oh, that's what I expected. So now, we put our recordings into the project folder. We already have there Marley, Vivaldi, and Metallica, as you can see, so we add our songs. We also have some empty main here, and some of my utils, for example, to show pictures, etc. Nothing fancy. Let's create a Python file, let's call it a dataset, where we define a class to handle songs loaded from a path on the hard drive. We will use Libroza library to load the songs from the given path, of course, as wave samples, recorded with a given frequency of sampling, and will be the number of samples, so the length of this wave. And let's create a plot method to draw such a song. Let's open the figure for 2 plots, and first we will show there our wave in time. Time is, of course, the index of samples from 0 to n, spaced with the frequency of sampling so that it is in seconds. And let's display the figure, and we are done. Inside main, of course, we'll just create an object to load our first recording from the path which we just put it in, and we'll draw it. Now we are about to see a few seconds of my recording, and we'll zoom in to 1 millisecond. Okay, we see it. We see a strongly distorted signal. This is due to the very poor laptop microphone. But it is a sine wave, I hope some of you see. We can see about 4.5 periods of a sine wave, which in this 1 millisecond window gives frequency of exactly 440 Hertz, so note A. To see it even better, let's draw an artificial note A. So note A 440, let's say a tiny wave with a frequency of 440 Hertz in time, but times 2 pi, because this is numpy in radians. We draw it, and let's run. Of course, we hard-coded 440 because we know I played A, and that's why our sine wave correlates so beautifully, as you can see, with the orange signal. If we wanted the computer to guess what note it was, we would have to generate whole spectrum of these blue sinusoids and calculate which one fits best into our orange signal. And actually, such operation actually exists, and it is called FFT, fast Fourier transform. Have you heard about fast Fourier transform? Some of you did. A little digression for Polish audience, so most of you. Like FFT, everything in any field has a 3-letter abbreviation, and I love them too, but please be aware when you're using 3-letter abbreviations, because sometimes you need to be aware and very, very careful. Let's calculate such an FFT spectrum for our song, and let's draw it. Of course, FFT returns absolute complex numbers, so we take absolute, we take FFT from NumPy, and we call it our wave. We normalize the values, and let's plot our spectrum and launch the program. And soon we will see the maximum around 440 Hertz. Here it is, and some harmonics. In other words, look at the laptop. She calculated itself. She calculated itself that 440 Hertz sine wave best fits the sound we played. We didn't tell her that, but she already knows. Let's load the second recording. Yeah? And on the right, you can see the maxima of the notes I played and their harmonics, but also now on the left, you can see I was hitting the string 4 times per second, right? And also, you can see more or less at 1 hertz, the periodicity of the whole thing is about 1 second, I mean 1 hertz. Do, right? So you can see everything. It's very cool. This means that the computer already knows what rhythm we played and what notes. So let's simplify it even more. Let's partition our spectrum into 5 intervals in the human audible range from 0.1 to 1000 Hertz and calculate average in these intervals. And this trivial function of mine will return 5 ranges and 5 average values. It is the embedding of our song. Instead of talking, let's just draw it right away for our third track, which is umcha, 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 the ska. And you can see umcha, umcha, umcha here, about 2.5 hertz, very strongly, this rhythm. But more importantly, in orange, you can see the whole spectrum averaged in 5 intervals now. Slow, medium, and fast rhythm, and the amplitudes of low and high frequency notes. So instead of thousands of samples, you can now have a 5-sample description of a song, and let's hope it is enough for us. Here is how it looks like for our training songs. You see different domains of music look a bit different. Each song is now reduced to only 5 white samples at the bottom. Now, the real neuron in our brain, while listening to Bob Marley, has some state, bias, and accumulates weighted signals from the synapses. And if the weights are trained properly, it activates accordingly, thinking reggae, right? Our artificial neuron, perceptron, will do exactly the same. We can combine it into a multi-layer perceptron, MLP. So we are about to load our song embeddings with the data loader which we just created, and we will build a sequential model consisting of linear multiply add module that will just multiply the inputs by weights and add them up, followed by a tan-H activation layer, which will return our result into a number from range -1, 1, so not reggae. A little digression here again. Tan-H is a very old activation function. This is how it looks like. It does the job. Equation not trivial, but surely very sexy. But today the world is dominated by ReLU. This is what the function looks like. It is just y equal x, but always positive. Nothing more. But the world has gone crazy. ReLU has penetrated into the world of pop culture and art. So that's it. Okay, we covered loading the song. Let's go back to our empty main. We will load songs compressed into 5 samples. The output of the model will be just one number between -1 and 1. And the training data loader will create song objects for Marley, Metallica, and Vivaldi, as we shown before. And before we create and train this network, let's just show ourselves this data in the console. So we'll iterate over our 3 songs from the data set and show X, which is the embedding of the song, and Y, which is its music gender, so 1 or -1. So we have it here now. You can see 5 numbers for Bob Marley song, and 1, because it's reggae. 5 numbers from Metallica and Vivaldi, both -1 because it's not reggae. This is not calculation, this is actually training data, so we know what is the result, and we put it here manually. So now we would like to write a model which will guess itself this 1 and -1, getting only the embedding of the song X. We'll show the results in a moment, but we need to create this model. As we showed in the slide, our one neuron brain is a sequential connection of a linear layer that receives 5 input samples and passes 1 output result to the activation layer tan-H. Let's add our layer definitions, alt-enter, alt-enter. The linear layer will take n in inputs and return n out outputs. These inputs will be multiplied by weights and added together. And we can have as many such multiply adders as we want, depending how many outputs we need. Initially, it will be just 1 because we are doing 1 perceptron. And the multiply adder is a piece of neuron that has bias and weights, as we shown. We'll define them soon. But first, let's define the call method, because calling such a neuron should return its initial state, so bias, to which we add all inputs x multiplied by weights w. So our initial state, we are adding the weight to our initial state, we are adding the weighted inputs from the synapses, and we return out easy. And now we return to the bias and to the weights. These should be just random numbers, right? In the beginning, our brain has no knowledge. It's like a baby that has nothing inside. So we could define them as floats, but right away, let's wrap them with some objects. Let's call such an object a value, and let's keep our original float in the data field. This doesn't help us anything yet. Actually, it just complicates things for us. Why? Because it's an object now, and it doesn't know how to add, subtract, and so on, because it's not a built-in float anymore. But we really need to be able to add, subtract, and so on. So we must define for our value add, we must define multiply, we must define negate, subtract, square, and of course tanh operations inside, because they will be useful for us. And now very trivial, of course, adding two values returns a value whose value is the sum of the input values, like trivial, right? And return result. Multiplication, exactly the same, but it is multiplication, so times. We'll define negation by multiplying by -1. Subtraction is the addition of the negated number. And a square, which just returns value squared, nothing fancy. And obviously tanh, which returns tanh. And we will use tanh function from the math module for this, okay? And now, let's call a list of multiple values a tensor. So user can initialize the tensor with just a list of values, but I write it immediately as a comprehension, because if they are values, let's take them as values, but if they are just scalars, let's wrap them into the values for the user, okay? And now, since we have our tensor values list, we can finally go back to multiply, add, and divide bias as a tensor of randomly initialized as some number, one number here, and weights, which we also draw randomly, but there are several of them, depending on the size of the neuron that is being created. And calling now the linear layer will, of course, call all of its neurons on a given input and return the list of results, one output from each neuron. And of course, we have a tensor, so we define linear as a return a tensor. tanh is a layer which activates tanh on all inputs and returns the result also as a tensor. And finally, very simple, sequential is just a concatenation of our layers, which will take each layer, call it, and pass it the result further on, and finally return the last result to the outside world. Now we run our program, and for each song we played, as you can see, we have Y predicted also, right? So, ladies and gentlemen, we created a program to predict music gender from a song. Are these results correct? Absolutely no, because as I said, we have a baby which doesn't know anything. She has an empty random brain in the beginning. So actually what it did, it answered, well, I guess it's reggae to basically any music, right? But we know it's random. So to analyze it better, let's define a constant seed for our random generator to be able to repetitively analyze our results. And let's calculate the loss. It is how much the baby owes us money for the mistake. And let's show it on the screen so that everybody can see, and this should motivate our baby to learn faster. How we'll calculate this loss? For example, as a mean squared error, very easily. Let's define such a trivial class which will take tensor A and B. For a start, they will be one-dimensional. So very easy. We just return their difference between these two squared, right? So this is the error. And we run to see, for example, here after the results are new because we just initialize random generator, but we can see a a very big mistake for reggae, so our baby owes us more than $3. That's what we expected, but now at least there's pressure. I asked you at the beginning for 10 zlotys per your mistake, and I saw this desperation in your eyes, like the strong motivation to succeed, to minimize the loss of your budget. We pass this motivation now to our neural network, okay? So we wrote foundations of our network. Let's refactor it a little bit so we have some structure. Let's create a package, as decent programmers would do. Let's call it framework, because it's a catchy name and it fits. I will create NN module, like a neural network, and a data module, and that's it. Value and tensor from our class will move to the data module, Control X, Control V, and layers and loss, these are neural network layers, so to the NN module, easy peasy, lemon squeezy. We fix imports because we need to. And let's put the import of our module and our tensor in the init of the package. And as my grandmother used to say, use it or lose it. Now, let's fix our layers, which are no longer available locally, because we need to get them from the NN module of our framework. And let's run it. But we expect everything to work the same, because it's just a refactor. So nothing should change, actually. And yes, nothing changed, so okay, we are so excited. We have our network return something. That's clearly the first step. But as we observed already, the network is stupid. So in order to make it learn anything, those random weights have to draw conclusions. They need to be aware of the mistakes and know how to fix them. So let's make a first step in this direction. Let our value not be just a float. Let's make it aware of what operation it came from and the operands which participated in that operation as parents. So here, for example, the resultant out is a value which knows that it was created during addition, and it knows its mom and dad. Value created during multiplication now knows who it is in the graph. This value will know it's originated from its single parent, very sad story. Hypertangent value will also know its roots from now on. What this gives us, attention and catch your pens please, because to my visualization we now add a model that is a graph, and since it's a graph, it can be shown. Ta-da! KK graph visualization. KK is me, hence the name. Nice? Now we're talking. If someone got lost, now they are found. Because where we are, we uploaded the embeddings to the network. This network has a random weights W, the blue ones. The network multiplied everything, added together, and got some result. After activation function, the result is minus 0.8, which, as you can see, differs a lot from our desired one, reggae. It differs as much as 1.8, which, when squared, gives 3.23, which is quite a big loss. So the network is angry, and no one wants to lose. But here we are. This is what we have written so far. What do we need now? We need to give our network some tools to decrease its loss, knowing that she can only control the weights. It cannot change the input data. It cannot change the laws of mathematics. The weights are its only parameters. That said, you have to know that when Chuck Norris trains the network, the input data is adapting to the random initialization. However, we don't have Chuck Norris. What we have is basic algebra. So let's try to figure it out. So how to reduce this loss by, let's say, 0.02, right? Our loss is the result of the square function. 3.27 was created while squaring minus 1, 0.8, right? So locally, here the slope is quite much. The derivative of square function is 2x. So at this point, it is almost minus 4. So to reduce the loss by this 0.02, you need to add to the first number about 4 times less, right, to the input. It is here more or less 0.005. Now how to increase this value by 0.055? It was created as a result of subtraction. The derivative of sum or difference is just 1. So to influence the result by 0.055, we need to just add the same amount to whatever input, right? Now this minus 0.8 is the result of the tan h function. Input here was minus 112, and the derivative of tan h is minus 1 minus tan h square. So here it is about 1/3. This is quite a small slope. So to increase the result by the desired 0.055, we must add more or less 5 times more to the input, which is about 0.015. Now minus 112 was created as a result of summing. The derivative of sum is 1. So here again the influence it just flows here the same, unchanged. And now finally 0.03 is the result of multiplying our weight by the input 0.3. And since the derivative of multiplication Cx is C, so it's 0.3. So actually to add 0.015 to the result, you need to add almost 3 times more to the weight. So about 0.05. Simple math, simple algebra, but let's check it. Let's check if we add 0.05 to one of the weights, will it actually make the loss decrease 0.02? Let's check it. So in our model, in the first layer, in our only multiply adder here, to the last weight, so the weight number 4, we add 0.05. And we run our predictions. Let's see the graph before and after. And let's run. Before 3.27, after 3.25, which is 0.02 less. Coincidence? I don't think so. Let's summarize. How changing any input influences its direct output? We estimate it as its local derivative. Very simple. And we can directly calculate it everywhere. Indirectly, we can calculate such an impact with a simple chain rule. For example, how do I influence the influence on the loss? How do I influence the influence on the influence on the loss? How do I influence the influence on the influence on the influence on the loss? And how do I influence the influence on the influence on the influence on the loss? Okay? And such estimation of the indirect influence of a given value on the loss is called gradient. And as you can see, we can calculate it by backpropagating the gradient from the parent up to the child. Okay? So our value now has the magnitude, but it also has a gradient and a backward function that will propagate this gradient backward to its parents. And as we have shown, it receives this function when defining the parent operation. If it was addition, then derivative of addition is 1. And this defined backward operation will be given to the out object created here when addition is called. And as we explained in the chain rule, backward will compute the parent's gradient as the local derivative of the operation multiplied by the gradient it will get backward from the child. So our sum has 2 parents, so the gradient will propagate in both directions, of course. And let's paste this into each operation. Okay, let's just copy and paste it everywhere, and we will just replace the derivatives. Like, for example, for squared, the derivative is 2x. For derivative of tan h is 1 minus tan h squared, as we said, and so on. And okay, we call backward on loss, and we will look at KK visualizer. We run it forward and backward. And in orange, we can now see the gradient for each value. So we know how changing each value will affect the loss. So easy, let's update these parameters. By parameter, I mean each weight and each bias of our model, so the parameters that can actively change. So to reduce our loss, let each such parameter go down by gradient by just a little, because it's a nonlinear function. And let's go forward, backward, update, forward. Wow, you can see what happened. We have loss 0.09 only. Prediction 0.7, which is almost 1. Our model has already tuned quite significantly into Bob Marley. Easy, man. We played Bob once, let's make it listen to Bob 4 times. I could listen to Marley all the time. What is 4 times for the machine? 1, 2, 3, 4, and prediction. Look at that. We have 0.91, which is almost 1. This neuron will kill itself for Marley, and I respect that. If we train one neuron, let's finally train the bigger network. 1, 2, 3 additional layers. In the first, 2 neurons, just for fun. In the second, 4. And only in the third, 1 single neuron calculating the output. Now you don't know this, but at this moment, KK visualizer in the background automatically is submitting a ticket to IT to purchase bigger monitors, you know? Bigger monitors would be fun. And I love watching the network learn like any parent, you know? A larger network, as you can see, the loss is a bit bigger. It's harder to train, but it will embrace much more knowledge. So let's finally show it other 2 songs by not breaking after Marley. And let's disable KK visualizer and just look at the console, but it's going to be bad. You will see it, it's going to be very bad. The last iteration, look, on Marley we have mistake for $2.5 again. Let the model pay and let him listen more. 40 times, enough? Imagine you play someone Marley and then Metallica and Vivaldi, and after 40 times you ask, you got this? And they say, no, we don't. $2.2 again. My grandma would tell him, listen, you should learn, little boy. Give him 100 times. And now it will be fine. It will be beautiful. Look at that. We have, I'm telling you, we have 0.9 on Marley, minus 0.9, minus 0.9 for Hetfield Vivaldi. The loss is less than a penny. Very cool. But behind this smile, there is a bit of embarrassment. After 100 times, when the music ripped off your brain, the guy suddenly like, you know? Why? Why did it take so long? It's simple. Because mean square error loss is not suitable for classification. Much better is log loss. For example, such a mistake here by 10%, as you can see, is irrelevant, totally irrelevant. Here, for example, if someone admits he guesses almost 50-50, we will not cut his hand for that, okay? I think this is a perfect example even here, because when Marley fans get really engaged into the music and the culture, for them, Vivaldi and Marley start to seem almost the same. But now, if someone swears with his right hand that he's right, while what he's saying is a sacrilege, they will pay. They will pay with their right hand. So, should we code log loss now? Nah, boring. We had enough. We'll do something else. So attention, catch your pants again. I will delete our entire framework package. Gone, delete it, red import, let's comment it, red almost all around me, nothing works, panic, oh my God, now look at that. In place of our framework, let's import PyTorch. Nothing screams. Does the almighty and mysterious PyTorch have identical interface? What just happened? We were writing our own network from scratch, like some students. Students, I respect you very much, learn hard, and I invite you to my professional network. And what we got? We got identical results as PyTorch, and identical interface. So actually, somehow, we wrote basic PyTorch from scratch. Conclusions? frameworks are no magic. Really, you can just click into whatever function, and you will see exactly this, exactly what we wrote. Actually, there is much more there. What is cool, in PyTorch, we have a lot of ready-made things, and you don't have to write them anymore. So I'm showing you a diff now, what we have written so far versus the version we would have in just 5 minutes from now. The most important is, of course, changing the loss from mean square error to cross entropy. But if someone wants something else, just control space, and the choice here, as you can see, is quite large. We are making our network bigger to understand more. So you see there were few neurons. Now there will be much more. We changed the output size to 3 to distinguish all 3 music styles. So not reggae anymore, but reggae, classic, or heavy metal. And we throw out our SAD data loader and put a beautiful PyTorch data loader, which itself iterates through subfolders with waves on our hard drive. We will use Xan dataset with songs that I downloaded from the web. A small digression again. I love, are you clean coders here? Any clean coder? No? Don't worry. I love super intuitive names. I love super intuitive names, like data sets with waves in separate directories per gender, beautifully organized. I would probably call Xan. Hence the name. We run this, and this time we evaluate our model every epoch with a collection of songs that the model has never seen. And after 100 of epochs, look at this, the model can correctly distinguish gender for 93% of the time. The data set is really bad, so that's pretty good result for a network written so quickly. And absolutely the most important thing at the end. Are you ready? .CUDA. One little word that you add to the model and to the data, and the whole thing suddenly moves into space. Or to be more precise, into NVIDIA GPU. Oh my God, it already finished. Buy GPUs, move your models to CUDA, train like pros. Otherwise, don't say, I haven't warned you. We simplified a lot, but if someone would like to learn more, I recommend materials on the web, especially the NVIDIA developer program. What we did, we wrote multi-layer perceptron from scratch for a foretaste of real deep learning products. I invite you to the NVIDIA deep learning examples repository, which I personally take care of. It's open source, just hit it, leave a star, fork, have fun. We have quite a lot of models out there. And on NGC, NVIDIA GPU Cloud, you can also download pre-trained models for everything. Of course, perceptrons are just the beginning. Deep networks can be convolutional, like, for example, here in Black Mirror movie series, where a neurosurgical procedure was performed on our hero to segment his vision to remove people from what he sees. A very nice, promising technology. Anyone can do such segmentation themselves with Mascar CNN, fill the background with the in-painting network, and apply some fancy blur at the end. Very simple. Here is the effect. Not neurosurgery, but augmented reality. And however, not fiction, but actual scientific experiment. I call it ignore level master. Special architectures have been developed also for graph analysis. Graph neural networks, GNNs, can be used for combinatorial optimization, relational analysis, graph generation, point cloud analysis, and many more. Transformers, which dominated language modeling, GPT, is basically based mainly on transformers. Reinforcement learning to train agents such as robots, self-driving cars, etc. And it could be treated as a different dimension of deep learning, but still it's policy gradients, Q-learning techniques are either based on backpropagation or entirely implemented as such. Finally, interdisciplinary models like NERF, which receives images as input, but processes them into spatial relationships and generates a 3D point cloud of amazing quality. Personally, I'm really excited about it because my colleagues from America did it. So you can touch me. All the mentioned models from various domains are today being introduced together to amazing tools, like, for example, Omniverse here, where you can perform compound text and image search for an object that can be turned into 3D models, obeying the laws of physical virtual world, which I feel is quite amazing, all of this together. And finally, a quick mention about GoGAN, which is another very nice example to show today's trend of interdisciplinarity. You write a sentence, for example, sunrise in the mountains, and the AI generates sunrise in the mountains, or how it imagines that. If you say, hey, I want more mountains, you can add a segmentation input layer. You can see my talent for drawing might be too much even for AI to understand. But here it is. Sunrise in the mountains drawn by KK. GoGAN 2 understands text, image, sketch, segmentation, so already quite a lot. Soon, this could be your gestures. This could be your whole life history fed into a recommendation engine from your Facebook account and, I don't know, your Biedronka loyalty card. Are you ready to see GoGAN draw a picture of you? Think about it and imagine the possibilities. So we started with the in-depth explanation of backpropagation, and almost everywhere here, the learning process is implemented with backpropagation. Plus, of course, various mathematical tricks and theories to make gradient flow efficiently through bigger and bigger networks and more complicated architectures. And now, the biggest players in the industry are, they need to make sure that the deep learning solution that they create keep up with this ever-growing technical advances and demand of the consumers. And one slide, what does it mean? Models are trained in different frameworks using multiple libraries. And all of this is maintained by different teams at various cadences. On top of that, data sets are growing in sizes and variance. Companies are constantly retraining the models on them, and then to provide inference services to a growing number of end users. This results in ever-growing demand for resources and means for the scalable implementation of AI solutions in various fields. And last but not least, hardware is designed and released to meet these dynamic demands, and we have a picture of industrial scale deep learning ecosystem, which should be taken care of, and for which continuous integration, continuous delivery is a challenge on a completely different level than the one we got used to in our traditional IT world. This is something I personally do in NVIDIA at a global scale. If you are interested in this topic, I will be somewhere here drinking coffee, so feel free to join and have a nice chat. Okay, we live in crazy times. I think many of you have heard that many great people actually are now signing petitions to stop working on deep learning models because, as a society, we are not ready for them. I think most of you have heard about this. Now, is there anything to be afraid of? Computers will not declare war on us, okay? But let me show you something that makes me feel anxious. We browse to NVIDIA Playground website, post a photo with friends or family, and delete a few pixels here and there, and we watch how machine imagines that. Computers will train themselves on all the data available in the abyss of the internet. In this case, I have no idea what data this network was trained on and what it knows about us, about me in particular. But it is a little worrying for me and embarrassing to say that for me, the generated partner is always an Asian. Thank you very much.
1, 2, 3.